All right, so we just started with our first example, okay? So this is self-test 7.15b. So Nate, what page was this on in the book? Okay, welcome, Ryan. Ryan,
You're
I'll mark
talking
you
to
here.
me? I don't know, Dr. J.
Okay,
Hold
that's
up.
cool.
I can find it for
It's
you.
page 293
Okay,
or
293, thanks.
273.
Okay, 273,
273.
perfect. Thank you, Renisha. So we're just trying to figure out what the enthalpy of combustion of diamond is. Okay, and so it turns out, and I'll erase some of this stuff that just kind of gets in the way. It turns out that the heat of formation, and we're doing all this from heats of formation, so the heat of formation of diamond is 2 kilojoules per mole. Oxygen, by definition, has the heat of formation of 0 kilojoules per mole, and of course, all of this is at standard state. That's why we have this little not operator there. And then you've got CO2's heat of formation is negative 393 kilojoules per mole. Okay, and I could round that up to 394, but whatever. So the overall heat of formation, enthalpy of this reaction is negative 393 minus 2, which equals negative 395 kilojoules per mole. And again, if we've been a little more accurate with our rounding, we'd be at negative 396, but we'll call that okay. All right. So any questions about this one? I feel like somebody just hit me up in the chat. No worries, Ryan. Good to have you, bud. Welcome. Okay, so I'm gonna go ahead and erase this board in 3 seconds. So take a screenshot if you're having a tough time. Otherwise, I will post this lecture sometime later this evening. So board gone in 3, 2, 1. Okay, so let's move on to example 7.14. All right, so this is kind of a long one, and blow up the screen a little bit. Yeah, it just isn't, man. It was actually easier when it was smaller. Okay, so I'm just trying to get as much space as I can on the screen. So there we go. So example, that just gives me a little more space to show some work at the bottom. So I copied the answer in here because we're actually going to use bond enthalpies to estimate the energy of this reaction. Okay, so what in the world's going on? Because we haven't done one of these problems before. So this must look like something new and maybe a little frightening. But don't worry, it's going to be all right. So, okay, so using mean bond enthalpies, okay, so calculate the enthalpy of the reaction between gaseous iodoethane and water vapor. Okay, so they really picked a big reaction for us to deal with here. But we're going to use these bond enthalpies. All right, so the first thing we have to know is how many of each type of bond there are, reactants versus products, okay? So let's just get that out of the way to begin with. So in the reactant side, you've got 1, 2, 3, 4, 5 CH bonds. On the product side, you've got 1, 2, 3, 4, 5 CH bonds, okay? So the mean bond enthalpy for a CH bond, as shown in the table, is 412 kilojoules per mole. But here's the beautiful part. There's no change in CH bonds from the reactants to the products. We have 5 on the right side, 5 on the left side. So we can ignore that, okay? Those aren't gonna break, those aren't gonna form. So those are out. We're not worried about that. Those are not bonds that are breaking or forming. We don't have to consider them in our treatment of this problem. Okay, so what is breaking, what is forming? So here you've got, so it's probably easiest to just draw this thing out. So you've got C dash C dash 1, 2, 3, H, 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 whew, and this is bonded to an iodine. So there's a carbon iodine bond right there, and then plus H2O, so O, H, H, right? And this is going to yield, and I'll put the results down here, or the products down here. Holy smoke, so that's going to produce, okay, and I'll extend that arrow through. Okay, that produces C dash C dash OH, H, 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 H. Okay, plus HI. All right, so what overall has changed, right? So that's what we really got to figure out here. So first off, we look at this situation. we look at this bond, this carbon iodine bond, this C, what the heck? Oh, I want pen there. Okay, this carbon iodine bond has gone away. Okay, that bond has broken. And it took energy to break that bond. Okay, that's the scoop. So we had to break that bond. And then we've got, yeah, because it's those things plus. That's crazy. Okay, so then you've got this bond over here. You've got this OH bond that also breaks. Okay, and then what we do is we form this CO bond and we form this HI bond. Okay, and a question for you guys, I actually forgot this myself, so remind me, scholars. These enthalpies here, are these the energies that are required to break the bonds, or are these energies of formation of the bonds? I don't remember what the convention is.
I think they said the
Formation.
amount of energy to break the bond.
That's the, okay, enthalpy formation. Okay, it's the amount of energy to break the bond. Let me just double check that in the notes. Or in the chapter here is what I'm looking at. I just want to make sure I get that right, because I remember this being not difficult. But like if you goof that up, you're in trouble. So
Hey,
You
Dr.
need to
J,
break a bond, yeah.
okay,
Why-
so okay,
why
in
is-
other words, bond formation is exothermic, bond breaking is always endothermic, is what the book says here. So breaking bonds, bond enthalpies. Okay, so all bond enthalpies are positive because heat must be supplied to break a bond. Okay. Yes, that is what I'm talking about. Okay, very chill, very chill. Okay, so all these numbers that we have in our table are positive because that's what's required to break the bond, right? So this is what you do, okay? These bonds over here form. So the bonds in the product form, right? So they're actually negative quantities. So HI, if you look at if it's in the product, it's negative. Guys, do we have something in here for HI? I don't see HI here. How are they gonna do us like that? They give us this thing to do and they don't show what's the bond enthalpy for HI. Go ahead, Antonio. What's the doggone it? That is just a dirty thing to do. Like, why would you show me this and then not show me the bond enthalpy that I need to solve the first problem? That's a brutal thing. Okay, let me look at the book really quickly. I'll find this. It's got to be in the book, or it's some HI bond is weak. So what is this? What's the bond enthalpy?
So Dr. J, Jacob asks a really good question.
Give you an HI. Yeah, that sounds okay. That sounds great. So 299. So this one is negative 299 kilojoules per mole. Okay, so negative 299. And then the CO bonds, that should already be in our problem though. Everything else should be there. That's a brutal thing. What's the question, Caden? What's the scoop?
Oh yeah, so Jacob asks a really good question. Why are the breaking of a bond and formation of a bond have separate enthalpy? Shouldn't they just be the same but of opposite magnitudes?
Yeah, that's exactly right. That's totally correct. Yep, no doubt.
So they are the same, but they have opposite magnitudes.
Yeah, they are the same, but they have opposite magnitudes. So like when this CO bond forms, like we got a CO bond forming, that's the old textbook here says that's 360 kilojoules per mole. So we're losing. So there's no way to keep this thing from being all crowded. So we're losing 360 here. Okay, or 360. So basically, to form these two bonds, okay, you have 360 and 299, right? So you add those together, and that gives you what the book gets, right? Which is negative 659. Okay, so negative 659. Okay, kilojoules. Okay, and then on the other side, you've got CI forming or CI breaking, and that's 238. So that's positive 238. And then you've got OH forming also, or sorry, OH is going to have to break, and that's a tough one. That's a strong bond. So that's 463. So you got 463. Okay. So you add those two up, and when you add those two up, you get exactly what the book gets. You get 7. So you add these two up, right? Plus this other thing, that equals 701 kilojoules. Okay. So, okay, old Dr. J knows what he's doing. So that's what happens. So basically delta H is estimated at 701 kilojoules minus or plus negative 659 kilojoules, which equals 42 kilojoules positive, okay? So this reaction consumes heat. It takes some heat to make this reaction go, because that OH bond is very stable, okay? That's the big thing. So even though the CO bond is really stable, the OH bond is even more stable. Okay, so, whew, all right. So that was a little bit right there, okay? We just kind of went on a magic carpet ride through bonds breaking and bonds forming and estimating the enthalpy of a reaction. So I've got some questions for you, but first order of business, I just want to know what your questions are, okay? Because that was a decent amount of material. Okay.
Sorry, Dr. J, I have a question.
Yes.
So basically,
Yeah, that's fine, Ryan. That's
it's always a heat required to break a bond, but like, let's say this reaction was like in reverse. So would the answer be negative or would it still be positive because of the fact?
Yeah, no, the answer would be negative because look, so you take whatever numbers are in this table and you give them a negative sign, right? If they're in the product, okay? So like if you look at, I don't know why this thing doesn't want to, I don't know what. If you look at the signs that we gave these numbers, we got negative and negative, right? And why do we have two negative signs? Because the CO bond and the HI bond were being produced, okay? So because these bonds were being produced, we gave their values negative signs, okay? Forming bonds releases energy, exactly as much energy as it takes to break the bonds. So these bonds over here were being broken, so we used the positive values that were in the table, okay?
Yeah, that makes sense.
Perfect. Yeah, and this is really useful stuff too. I mean, like just by knowing bond enthalpies and by measuring pretty simple things, what you can end up doing is getting good estimates of what's going to happen with much more complex chemicals that are maybe even hard to obtain in quantities large enough for you know, like basically calorimetric experiments. So, you know, like this is really good stuff to do. So what's going on here? Okay, so what are some of our questions? Let's just take a couple minutes to like surface some questions. I want to know what your questions are. So Rainisha, that was a great question. Who else has a question?
So is there any way to determine mean bond enthalpy other than experimentally?
No, you got to do it experimentally. I mean, I'm sure there are like some you know, really good physical chemists who are interested in that kind of thing and doing it computationally, but this stuff was all determined experimentally. Everything in that table determined experimentally.
Okay.
Yeah, we'll eventually have computers that'll cook all this up, but computational algorithms that'll do all that. But you know, I don't know to what state that stuff has advanced. I just don't know.
Right.
Dr. J, I have one last question. So
Yeah.
is it always going to be the case where bonds are breaking?
Well,
Or is it
again,
always gonna...
the bonds in the reactants are breaking. The bonds in the products are forming.
Okay.
Okay, so the bond enthalpies are positive in the reactants and they are negative in the products. Okay.
Yep.
All right, any other questions? Okay. So again, this just allows us, this is like really convenient because we can just use bond enthalpies to figure out, you know, the enthalpy of whatever reaction we want, right? As long as we have all the bond enthalpies for all the bonds that are breaking and forming, we can calculate the enthalpy of any old reaction. That's tremendously powerful, okay? That tells you a lot about what's happening in that reaction, and especially a lot about whether that reaction is going to proceed or not, okay? So, all right. Whew. Okay, may I erase the board, scholars? Okay, I'm going to erase the board. Take a take a picture if you need to, a screenshot, but I'm gonna erase it in 3, 2, 1. Okay, bye-bye board. Okay, so next example, we were at 7.14, and I think that's what takes us to 7.18a. Okay, so I copied that bond enthalpy table there, right? And now you're gonna go ahead and try one of these on your own. And the Lewis structure is gonna be really important here, but also just kind of keeping general track of what's happening, right? So I'm gonna give a little rundown here. So there are 3 carbon chlorine bonds in the reactants as in the products, right? Nothing changes there. Okay, so that's not important for us. So then what does change? Well, we had 2 HFs, now we have 2 HCl's, right? So there are 2 HF bonds breaking and there are 2 HCl bonds forming. And why in the world, like, that's not included here? I don't know. So I'm gonna have to Google and get you that information. So you know what? Skip this. Okay. Or was that a dumb thing to do? Let's see. Might have been dumb. Then what's forming? You've got 2 CCl bonds. Okay, Brianna. 2 CCl are being broken and 2 CF bonds are forming, right? And so those we actually do have. We have CF and we have CCl, okay? So those ones are here, right? But we need HCl bond enthalpy and we need HF bond enthalpy. So let me go ahead, let me go ahead and Google those for everybody really quickly. So HCl bond enthalpy is
Althea.
okay, 427 kilojoules per mole. So HCl. So HCl, and I'll show the bond. And then what's the HF bond enthalpy? HF bond enthalpy. HF, okay, it's right there. HF is, whoa, 500, yeah, 565 kilojoules per mole. Okay, so good luck. And I'm gonna do this calculation too to see if I get the same answer, okay? So that's the deal there. All right, so give this a shot. Let's take 4 minutes to knock this one out. So hey Siri, set timer for 4 minutes. Hey Siri, set timer for 4 minutes.
Okay, 4 minutes and counting.
Okay.
Dr. J, is the HCl bond 427?
Yeah,
Okay.
yeah. The answer I get is off by 2 kilojoules from the book's answer, so that's okay. One of these answers is just rounded a little. One of these values is just off by 1. That's cool. Okay.
Hmm. Yeah, I got minus 16 kilojoules per mole.
I got 26.
26. Huh.
If you do 484 minus 338, you should get
Right.
146, right? And you multiply that by 2, that gets you 292. And that's
Right.
negative, so negative 292. And then
Uh-huh.
on the other one, oh no, you're right, because it's negative 292. Yeah, you're right. Yeah,
Or
negative
so-
16. Yeah, I got negative 16. You're right, Caden. That's right.
Okay,
I was off
cool.
by 10. You're right.
All right.
Yep. Negative 16. That's what I get too. So one of these values is a little bit off. That doesn't bother me. Okay, so I'm going to fix that. So with our values, you should get negative 16 per mole. Okay. Cross that out. Negative 16 kilojoules. That's what we should get. Okay. So we'll just go ahead and let folks work on this. And guys, if you have a question, if you're totally stumped, what I need you to do is reach out, okay? Send me a chat, start talking to me, whatever it is, because we got to get everybody on track, okay? This stuff is pretty straightforward, but you know, if you're like unsure about the process at first or something like that, then we got to get on it right away. Good. I just saw a couple. Okay. A little confused. Okay. So a couple of us are a little bit unsure about this. Okay. All right, so a few of us are unsure. Okay, so let's just go ahead and like look at what's actually happening here. So I'm gonna start erasing some of this stuff. Actually, I guess I'm not. So here's what's happening, okay? So you've got this, this situation, right? And here's what's breaking. You've got, this is the business end of the molecule. So you've got a carbon, right? It's bonded to a Cl, it's bonded to a Cl, it's bonded to an H, and it's bonded to the rest of the molecule, okay? Plus 2HF, right? Which just means, like, I'll just draw them out. So H bond F, H bond F. And what's that making? Okay, that's going to make C bonded to F, bonded to F, bonded to H, bonded to, again, the rest of the molecule. And then you've got another HCl, another HCl, right? So two of these bonds are forming. Okay, that means you've got to multiply this number here by -2, okay? Because we're forming these bonds. So this energy, this 427 kilojoules, is released, okay, in the formation of these bonds. And over here, these two bonds are formed, these CF bonds. So you got to take this particular value here, okay, and you multiply this guy, okay, by -2. All right, because you're forming two of that guy, okay? So that's what goes into your products. And then your reactants, right? You have two of these guys, okay, times 2, and then that's a little whack to do it like that, so get rid of that circle. So this guy here, you multiply it by +2, right? Because you're starting with these, and you got to break these bonds, so it takes that much energy to break them. You're also breaking these HF bonds, so you're also going to multiply 565, multiply that by +2, okay? And so when you do the math, what you end up with is the CCl bonds, that's 338 times 2, so 338 times 2 equals positive 676, okay? 676. And you also have, these HF bonds times 2. So you got 565 times 2. That's going to give you 1,130. Okay. And you add these guys up. All right. So you add these guys up. Okay. And you're going to get 1806 kilojoules. Okay. And then we got this other situation over here. So you've got two CF bonds. Okay. So that's 484 times 2. That's going to equal 800, 968. So 968 kilojoules. And then you're going to have this other guy times 2, and I'm going to have to erase our answer really quickly. Okay, so you're going to have this guy over here, multiply him by 2, so HCl bond, that's 427 times 2, so that's 854. So 427.
Isn't it negative?
Yeah, thank you. So that's right, negative 427 times 2. That's negative 854. Okay. And then that's what you get there. Okay, good. So what's the deal? All right, so you produced, okay, negative 854. Okay, now you got to add these things up, right? So when you do that, you get 900 and 800, that's 1700, plus these guys go together, that's 1922. And then you had, what was your original number that we got when we added those together? So that was 1906, right? So you wind up with, man, this is just wild. So you had 1906, right, positive, and then you have over here negative 1922. And if you add negative 1922 to positive 1906, you get exactly, okay, negative 16 kilojoules per mole.
I thought it was 1806.
No. Or did I get 1806? Not 1906? 17.
You got 1806.
1806, yeah, that's right. So it looks like I made a math error somewhere. There's a lot of addition. Except, yeah, 676, that's right. And then 565 times 2, that's 1130, right? Because that's 1,000 plus 130, that's right. And you add those two together, you get 1730, 1806, that's correct. Now, how about this other one? So 427 times 2, that's 854. Okay, did I get my 854? I did. And then 484 times 2, that's 968. You add those two together, you get 700, 1700, then you get 1800. Okay, so I made that mistake. So it's 1854, 1822 instead of 1922. So those should have been those. So the answer is the same, but I was off by 100 in both cases. Okay, so 1806 and then negative 1822. All right, and then you add those two together. Thank you, Shifa. You add those two together, and then you get negative 16 kilojoules per mole as your final answer. Okay. Okay, so that seems brutal, right? And the reason it seems brutal is that I literally can't write all this information on the board. Should I start this on the on sort of like a different like whiteboard so you can see it a little more clearly?
I'm
I'm trying to understand, but it's the format. Let me help you. So let me just get rid of that. And then, Caton, are you on hand with the numbers? Can you be handy with those for us, please?
Yeah, sure. Okay. So just the numbers with the mean bond enthalpies or the addition?
Yeah, the mean bond enthalpies and the
Okay.
addition, subtraction stuff. But I can go through that pretty quickly, I think.
Okay.
Let me go through. Oh, I need to be able to share a different thing.
Hmm.
Let me go to a new share. So new share. Let me just show you a whiteboard. So the problem is you need to see all this stuff
Yeah, let me open it.
organized the right way. This is not hard. This is just a bunch of addition and subtraction. So like if we're legitimately confused on this, I feel sorry for all of us, but we're not. We're not confused. Okay, so let's look at the chemicals. Okay, let's just look at the reaction. So I might have to write this out in 2 whiteboards. So you keep notes on paper, okay? And I'm going to keep notes best I can on the whiteboard, okay? Because this is totally not passes. Like I'm telling you right now, the stuff we've done this year has generally been way more complicated than this. So like you're gonna get this as soon as you really see what's going on. So okay, so you have CCl3, and then what's the rest of the chemical, Caton?
So it's CH3, CH2. Oh, wait, looking at the wrong thing. Was this the one with water and H? No, it wasn't. Oh boy. Okay, maybe I'm not on hand with the numbers here.
7.18a. Okay, I got it. So CCl3, CHCl2.
2HF goes to CCl3, CHF2 plus 2HCl.
Okay. Okay, so is that reaction cool? Is everybody cool with that reaction? Can we see that reaction, say to ourselves, hey, that's a reaction. I get that. Is that okay?
Mhm.
But I want to hear from everybody, like Idali, Ryan, Brianna, how are we feeling about this? Mercedes, is everybody okay with that reaction? Can we see that reaction? Does that reaction look okay?
Yeah.
sir.
Okay. So it's a reaction. Now the first thing I'm going to do I need to draw this out in terms of like Lewis structures so you can see which bonds are breaking and which bonds are forming, or are we past that?
I'm good.
Jacob, you're good? Idali, Antonio, Ryan, what do you guys think?
Can you please?
I'll
Yeah,
draw
can you
it.
try it again?
Okay,
Yeah.
so here's what happens, right? So okay, I'm going to use skeletal structures, but you have Cl, Cl, and then I'll make it all a little bit neater because I just want to make sure I can fit it all on the page. Cl, and then you have and then you've got CH. So you actually don't, man, that's ugly as sin too. Sorry, it's just ugly. I'll draw it out I'll draw it out with proper Lewis structures. So Cl like that, and you got C, H, Cl, Cl plus HF, HF yields Cl dash C. Okay, that's as good as that gets. Okay, so so 2 copies of HCl. So we need to figure out what's going on here, right?
Mhm.
So here's what's breaking, here's what's forming. Okay, so these bonds right here, and these bonds here, okay, are breaking. And then these bonds here and these bonds here, okay, are forming. Okay, forming. Okay, forming. Those bonds are forming. All right, so what does that mean? So the delta H for the reaction, and this is something I'm going to erase probably in a second. So equals the sum of the bonds forming, or sorry, bonds breaking, because it takes energy to break bonds. So the sum of the bonds breaking. And in fact, let's just get rid of the summation notation. That sucks anyway. So it equals the total of the breaking. So the sum of the breaking, and you can tell that when I write breaking, right? Minus forming. Forming, okay? And this is delta H breaking minus delta H forming, okay? That's what's happening. So what does that turn into? So the breaking is gonna be 2 times the CCl bond. Okay, what is that, Keaton? 338?
Yeah, so CCl bond is, let me tab back over.
Good, and then HF is 547 or something?
565.
565, okay. 2 times 565.
Mhm.
Okay, minus, right? What's the HF, what's the CF bond?
The CF bond, oh my goodness. CF bond is 484. Mm-hmm. And the CCl bond is 338. Okay, yeah, good.
What? No, the HCl bond. I need the HCl bond.
Oh, HCl bond is 428.
Okay. And all of that comes out to negative 16
Mhm.
kilojoules per mole.
Right.
Okay. Woof. All right. Okay. So does that help? Does
Wait,
that
Dr.
provide a
J?
clearer picture of what's going on?
Yes, that
I'm
makes so
con-
much more sense.
Yes, it makes sense.
Yeah. Okay. Shifa, how are you feeling? Shifa?
I feel I feel good. I'm just like finishing my writing.
Okay. But this, once you see it presented this way, this makes sense to you, yes? Is that correct, Idali? Does this make sense now?
Yeah, it makes sense because it's neater and I can see all the numbers.
Yeah. We're running into like a whiteboard problem, okay? So like, welcome to, our new normal. And then, Ryan, does this make sense now?
Yeah.
Okay. Antonio, how you doing?
All right, just the numbers like 565 and 338. You got those from the chart, right?
Yeah, you got to get those from a table or you got to look them up.
Yeah.
You got to
Oh.
look them up. You just got to look them up. Okay? So the chart will help you or you got to look them up somewhere. I'll put them on the problem. When we do these problems again, I'll make sure that they're just ready to go for you. Like that's the whole, like this thing is a little cumbersome. Like I really miss the big whiteboard right now.
Yeah.
Yeah.
I've been having that all day with AP Chem this morning, or AP Calc.
Yeah. What it means is I just need to go out and get one of those iPad Pros maybe, or I've got a big laptop that I could use with like an HP pen. Or
Yeah.
the other thing I could do is I could maybe get one of those like Apple pencils or something. I don't know.
Dr.
But
J,
iPad Pro would help. Yeah. What's up, Jacob?
what if you got your own like whiteboard and then just present it in your house instead of on
Nah,
screen?
that would suck. I don't have enough room. Like that just wouldn't work right.
Okay.
Can't do it. Yeah. I thought about it. That would be great to be able to do, but I just can't do it. Ugh. It's like I'd have to throw my dogs out or something. They wouldn't like that.
They don't take up that much space.
No, I'm kidding. Oh, okay.
Dr. J, you know what you've forgotten for several days?
Well, I know. I owe you guys shoes, don't I?
Yes.
Yeah, I know. I got a pair right here, okay? I can show you. It's a good pair.
Okay. So Dr. J, but before we go to that, are there questions like this on AP Classroom? Because like I want to get like the muscle memory of doing this process down.
Yeah, we're going to talk about that a little bit later. So let's just try to get some more examples, and then let's look at, because I haven't looked at the AP Classroom stuff. So we can start looking at AP Classroom basically after we're done with this chapter. There might be stuff from the next chapter that's in it, but we just need to get there.
So did they make any changes to the AP test at all?
Yeah, they did. So apparently it's only going to cover the material through like mid-March.
Yeah.
So I don't even know what exactly that is. And I don't know exactly when the exam is going to be held too. I think there's like you can take it on the normal date, or I think you can take it on a later date. I don't know. I guarantee you that whole thing is a nightmare right now. So we'll see what really ultimately comes down. But I got to talk to Dr. Zhu to get all the details. In the meantime, what I'd like to do is put together a really solid plan for us to all review over break. And so what I'm thinking the best thing would be for us to meet on a regular basis during break. And so that's my time and that's your time, but like it would get us there, like if I really honestly feel that if we just push hard through the break and keep going, what'll happen is we'll all be ready to go when the AP test actually gets here, because I'd love for you guys to get college credit, because I know you can understand the material. There's like nothing we've covered all year that you failed to understand. It's just a matter of going back through and reviewing. And with us missing 20 minutes a day over the last couple weeks, and then with this change, see, one of the things that actually is not good for us is that Unit 8, which we spent a lot of time on, that was acid-base equilibrium. I don't think that's even going to be on the test.
Oh,
so
right.
that hoses us, because we were ready to go with that material. We got to that early, and then we were going to just clean up this enthalpy stuff, because the enthalpy stuff is actually really simple. The acid-base equilibrium with all the squaring and the variables and the blah blah blah, that
like
gets
we
more
blend for
complicated,
that.
right? Yeah, but like our advantage basically got dashed on account of this coronavirus situation. So what we need to do is we need to meet so that we can really get sharp on this stuff. So what I'm thinking is we'll talk about this tomorrow, but we'll just set a time of day that would work for most of us, and then I'll record and I'll put lectures up, and you guys will just have problems to work through. And so by the time we're back from break, everybody will be expected to be sharp one way or another. But those of us who can meet will meet, because it'll help us all to get really prepped for that AP exam. Okay. And this is, I mean, again, this is going to be hours of my time that I'm taking away from my break with my wife and my dogs. And I don't get a lot of break time. But I think it's important. Right. And so I hope we'll all of us who can make that commitment. Okay. I know I'm asking a lot of you. But I'm asking a lot of myself and my family. And so I think that's the way to go. Okay. And if it's just me, myself, and Rainbow and Lollipop or whatever, and I'm like lecturing through material and putting up videos for people to do as homework, well, then so be it. But I hope that that those of us who are able will hop online and we'll get this stuff done. Okay. Because at this point, just reviewing as best as possible is absolutely in our best interest. Okay. So that's all I've got to say about that. If anybody else would like to say something about that, please feel free. Otherwise, feel free to shoot me a chat message or whatever. Yeah.
So is the meeting over break just going to be like how we're meeting right now?
Yeah, it's going to be just like this.
Okay.
Yeah.
Cool.
I'm going to be here. You're going to be
I'll be
there.
down to join, Dr. J.
What now?
I'll be down to join.
That's awesome, Sinead.
Yeah,
Thank
you can
you.
have as much of my time as you
I'll be
like.
there too.
Yeah.
Me too.
That's awesome. That's awesome. Yeah. You guys are the best. You know,
Well, thanks.
I'm really looking forward to this too. Like it's going to be one of those little things that I'll really like be happy about on a daily basis. I think what we'll probably do is just meet Monday through Thursday like we have been. And just set that meeting time for like an hour and 10 or an hour and 20 minutes or whatever, maybe an hour and a half, just whatever feels right for us to get through certain content pieces. Okay. So really most of it is going to be getting solid, really solid on all of this thermodynamic stuff, because that's the stuff that we put on hold to get to the equilibrium, the acid base equilibrium early. So we'll just be jamming on thermodynamics, and we may go into some other things. And then when we come back, it'll just be straight test prep, like, you know, right up until the AP exam date. So we'll have maybe 3 or 4 weeks to just really prep before that test. But we should definitely meet over break to whatever extent we can to just get solid on this thermodynamic stuff. Okay, so Ranisha just asked, can I explain why we use subtraction for the DH of the bonds? I thought it was addition. The delta H of the bonds. Okay, so it's a difference, right? So like you could add them, or you could, so basically I'm just adding negative numbers. Remember, it's so like you could call it breaking plus forming, where forming is a negative number. Okay, where forming is a negative number. So like if you say to yourself, formation by definition is negative, then you use a plus sign. Then you use a plus sign here. Okay, if you say to yourself, like it's easiest for me to think, like I just look at the table, and whatever bonds have formed, I subtract those energies that are written in the table, which are positive. Okay, so it's just it's however you want to think of it. Does that answer your question, Ranisha?
Yeah.
Okay, good. All right, let's try one more problem. So I'm going to clear this whiteboard here. And then let's try one more problem. So I don't know why won't this board clear? I don't know, the board doesn't want to clear. What the heck? Clear? Why? Okay, I'm going to stop this share. I don't know why. Then I'll give a new share. So new share, we're going to go right there. Okay. Symphony, Antonio, how do you guys feel about meeting over break?
Yeah, I can make it.
Okay, awesome, Antonio. What do you think, Symphony? Is that something you might be able to do?
Yeah.
Who tried this?
Okay, very good. Okay. Shifa, April, Mercedes, you think you guys will make it in? Marcella?
Yes. Yeah, I think so.
Awesome. Okay. April, Shifa, are we going to be able to Get you guys in here too?
What?
Are you guys going to be able to join too, do you think, for break?
Yes.
You guys are awesome. Okay.
Yep.
Okay. And I'm going to make sure that we're just super efficient and on point. So I'm going to get all the details, et cetera, and we're just going to jam on these things. So, so just as a review, just as another question. So this is working for us. This method of doing problems on the little notes sheet like this. This is better.
Yeah.
Okay. I'll try to get something even better put together if I can. Okay. Thank you, Idali. All right. So, okay. Does this CF and CH? Yeah. Okay. F2 and F2 is going to have, what's the F2 bond enthalpy? So, okay. F bond enthalpy. Okay, I just wish I had FF. That's 155 kilojoules per mole. Okay, so FF. So let me go ahead and get some of this stuff written on the board. So FF. So this is F dash F is 155 kilojoules per mole. So okay. And then use bond enthalpies, standard enthalpy, 1 mole of gaseous CH4 reacts with gaseous F2 to form CH2F2 and HF. Okay, so I think the thing that we have to do is we have to go ahead and get this balanced. So what you have in this situation is CH4 plus 2 F2s yielding CH2 F2 plus 2HF. Okay, so what forms? So you've got 2 HF bonds forming and you've got 2 CF bonds forming, and what breaks? 2 FF bonds break and then 2 CH bonds break. Okay, so go ahead and give this a shot. All right, do your best, and I'll be ready to go through it. In we're out of here in 9 minutes, so let's go through this in 5 minutes. Okay, so hey Siri, set timer for 5 minutes. Hey Siri, set timer for 5 minutes.
Okay, 5 minutes and counting.
Okay, I didn't ask Brianna. Brianna, are you good to meet over break?
Sure. Yeah.
Awesome. Okay, perfect. Yeah, I'm really happy. Okay, so okay.
So Dr. J.
Yeah.
F2, the bond enthalpy of that is going to be 0, right? Oh no, it's 155.
No, it's not. It's 155. Yeah, it's different. It's different. It's not like a standard state like formation enthalpy. It's not the same kind of thing.
Okay.
Oh, we don't have the HF bond enthalpy, except we do from last time. Kate, what was it, like 565 or something?
HF was 565.
Yeah.
I've got this link over here that has a lot of really great common bond energies. I'll just put it in the chat really quick.
Thank you.
Oh, I'll send it to everyone. There we go. Wow. So Dr. J, my answer here is strongly exothermic.
Yeah, exactly.
Okay.
I get 1998 subtracted from, what is it, 1154, 1134.
I get
1134. Yeah, 1134.
My final answer, I end up with 11 minus 1119 kilojoules.
I didn't get that much.
Okay.
No, because look, I did all this math in my head. So
Okay.
I got 565 times 2 is 1130. and then you got this these CH bonds. You got two of them. So that's CF bonds. So you're gonna form those. So you're gonna get 484. So that's 968.
Mhm.
So 968. 968 plus 1130 equals 2098. Okay.
Mhm.
And so you're going to lose 824 and you're going to lose 310. So I got negative 964 for
Okay.
that one.
Oh, it's products minus reactants, not reactants minus products, right?
Yeah, exactly. And it's a
Okay.
negative. Yeah, it's negative. No, it's reactants minus products.
Reactants minus products.
Yeah. It's
Okay.
reactants minus products, But I just did it the other way. And I know that I need to flip the sign of that 964. So I do in my mind.
Okay. I got magnitude error. Oh, that's right, because there's two F2 there. Okay, yeah, that makes sense.
Yeah, that's what it is. Yep. Okay.
Yeah, 964. Okay, we're good.
Good job, Jacob. Yep, that's right. Yep, that's it. That's what Kate and I got too. Nice work. Yeah, that's fine. Either you're off by like 6 or something. Don't worry about the rounding error. Good job. Good job. Okay. Okay, there we are. Okay, great. All right, so how much time do we have left? 30 seconds. Okay, so Shifa, Mercedes, April, Marcella, how are we doing, ladies?
I'm still working on it.
Okay, is it okay if I start going through the answer now?
Yeah.
Okay, so here's how this works, okay? So you have two HF bonds forming, so you multiply this by 2, okay? And you have two CF bonds forming, so CF is right here, 484, you multiply that by 2. So it's reactants minus products, so reactants minus products, right? That's one way to think of it, equals, okay, so let's go over here. So the F2, you got 2 of these, so 310. Okay, you got 2 of them. And then minus 2 CH bonds. So that's 412 times 2. So you got to add that up. So that's 824. Okay, minus, right? What are the products? Okay, so you're forming 2 HF bonds. So 2 times 565 plus you're forming 2 CF bonds. And the 2 CF bonds you can see over here. Okay, the 2 CF bonds are 484. Okay, and it might be a good idea to watch this again in the lecture if this seems confusing. So 2 times 484. Okay, and then all of that adds up to negative 964 kilojoules per mole. Okay, that's what you should get at the very end. All right, so okay, so I'm going to stop there, and then any quick questions for me while I get out a pair of shoes? Okay, so Ryan, did that make sense?
Yeah, that makes sense.
Okay, Antonio, you get that one too?
Yeah.
Okay, perfect. All right. Good. Brianna, was that one on point for you? You understood how that worked?
Yes, I did. It's great.
Okay. Awesome. Yeah. Because like I said, this isn't complicated. We're running into a board space issue. So you guys can just totally knock out these problems. So if you had any issues at all, guys, don't forget, I'll be here for office hours today, okay, 3:25. And then this lecture is going to be online if you'd like to watch it again, okay? This is not tough material for you. But right now what I'm going to do is I'm going to stop that share. I'm going to show you guys these shoes. So this is one of my newest pair of Jordans. These are the UNC to CHI, so UNC to Chicago. So it's got the navy blue from the University of North Carolina for the Tar Heels, and it's got Chicago for the Bulls. So Jordan played his his college ball at North Carolina, University of North Carolina, and he played, you know, his professional ball primarily with the Bulls. The sole is red, and then these are Jordan 1 retros. So they come with the original like Nike Air right there. They don't have a Jordan logo on them. They don't have the Jumpman because that wasn't introduced until the Jordan 3. And then they actually don't come laced. They just come with the tongue like flopping out like this, which is kind of cool. So you got to lace them yourself. Sometimes they come with extra laces. Did these? I don't see any extra laces here, but it looks like they come with a tag, which is pretty cool. Like that's cool. They've got this like little Nike Air tag on one of the shoes, which is cool. And yeah, just looks like one pair of laces. That's fine.
Those are
So
some nice pairs. I like them.
you like, you know, okay, so here's what's crazy. So I don't consider myself like a cross-dresser. Not that there's anything wrong with that, but these are actually women's shoes. So like these were designed for women. So these shoes are a 10.5 women, 9.5 in men. And so this was actually like a woman's shoe, but yeah, I mean, it fits just like it's a 10.5 women's, 9 men's. So it fits just like any of my other Jordan size 9s. So I like it a lot because I've always wanted the blue and red, and then I always love the light blue of the UNC Tar Heel. So I like
Yeah, I
it.
really like the light blue. That's like my
Yeah.
favorite.
I think they'll be easier to wear than like the royal blue. A lot of like Jordans have royal blue, Jordan 1s, but that was an OG color, but I like that light blue a little better. So
Yeah, I like the idea that you have to like lace up your own shoes. It's like a giant building their lightsaber.
yeah, and you can lace them a whole bunch of different ways. If you Google like different ways to lace shoes, it's just like endless. There are so many different things you can do. So, all right. So that's all. Okay. So Rainisha, take care. All right, everybody, take care. I hope to see a few people at office hours.
Bye, Dr.
All right.
Oh, Dr.
Bye,
J.
guys.
Bye.